Right.
Recording is started.
Thank you, Brandon, and thank you, everyone. This is my third lecture on my mini course in CTNT 2020 on computations in number theory research. And what I'm going to do today is do an overview of Magma. I haven't done it yet. I plan to post a basic video of more basic things in Magma than what I'm going to do today. Today, I'm going to do some Magma, but I'm also going to try to relate it to what other instructors are doing during their mini courses. So there will be a more basic approach to Magma coming up, but I'll do some elementary things here too, just to show you how Magma works. All right. By the way, so Magma is another algebra package, which is very nice. It is not open source like Sage, and it is not free like Sage. However, Magma, which by the way is distributed by the Computational Algebra Group at the University of Sydney, Magma is free in the US to eligible institutions thanks to the Simons Foundation. Right now, there is an agreement that goes through July 31st, 2022, and nonprofit public universities, public institutions in the US nonprofit, non-government, educational or scientific research institutions can get a free license to Magma. So myself, through UConn, we have, through the Simons Foundation, we have a Magma license, which is pretty nice. All right. You can do Magma if you don't have a local installation. If you haven't installed Magma in your computer because you don't have a license yet, you can still access Magma, and for all intentions purposes, you can do Magma just online. So I went from here in the Magma page, you can go to calculator, and it will bring you to an online calculator. So if I want to do some Magma code, I can go here and then just do that 5 plus 7 and submit it. And so I'm in the US, I typed 5 plus 7, it went all the way to Australia, calculated 5 plus 7 equals 12, and then sent me back the response. Still, though, it's pretty efficient. It's a pretty efficient system, and the calculator is something that I use also all the time. Just because, well, it's easy to look at things here and see what the results are. So here's the rank of an elliptic curve, 1, true. All right. So instead of, but I do have Magma in my computer. So instead of doing that, I'm going to use Magma here. I hope everyone can see that. All right. And by the way, feel free to interrupt me. I'm not looking at the windows with the chat, but Brandon will let me know if there are questions. I'm happy to answer any questions along the way. So here's Magma that is installed in my computer at home. The name is R2D2, and you can see the name of the computer, R2D2, and which has been acknowledged in some of my papers, thanks to R2D2 for the computations that were contributed to my paper. And this copy of Magma is thanks to the Simons Foundation. All right, so let's start with just a comment box in Magma. So I can type like this. This is a comment, and that Magma is going to ignore me. And you can also do multi-line comments in your code. So I can, all right, maybe I messed up already, like this, copy and paste. Okay, so that's a multi-line comment, just in case you want to comment something out. We can define the basic ranks. I have a cheat sheet here to just comment, to copy code without having to type too much, so I can get a little bit more done. That's how you define the integers, the rationals, the reals, the complex field. Difference with Sage is that you define things with column equals, like just like some mathematicians do in real life when you're on a blackboard. That's how sometimes we write definitions. So that's what Magma does. The language in Magma is a little bit different from Sage. It's I think a little bit more natural of a language. By the way, also, say integers or real field has those parentheses because it can take some parameters. So for example, in real field, if I say, what is the real field here, is a real field with precision 30, but I can change that. If I want to talk about the reals with 100 digits, then I can do so. Let me define the reals. So by the way, if I do arrow up, then I go to other commands I've already used, which is pretty handy. And I can define the reals, and then I can define pi. Pi itself, some of the constants, some of the most important constants are already built in. And if I do pi of this incarnation of the reals, then it will give me 100 digits of pi right there. All right, very good. So that's pi. It sort of broke the line somehow, maybe because my window is, it could be bigger, but I don't want to cover up the whole thing. All right. What else? By the way, I can, at any point, I can ask about instructions here. So I can query Magma for help. There are two versions of this command. So if I just go to one, then it gives me some explanation of what this command is. That's looking a little bit ugly. Let me try to fix it like that. All right. What else can we do? Just like in Sage, I can type, I can call Galois fields, finite fields of 25 elements, for example, or something different. I can do the ring of integers modulo 25. I can also call it like that. Okay, the integers modulo 25, and then if I do, if I call that R, that ring, then I can, for example, invert elements or talk about elements in the ring. To make sure that Magma understands that, say, I want a third, but a third considered as an integer modulo 25, so I want the multiplicative inverse of a third. Remember that in Sage, I would have done this. In Magma, I sort of yell to Magma, hey, this is in R. So you have to put an exclamation point that I'm looking for a third in the integers modulo 25. So when I'm at home and typing on my own, I usually yell at Magma like that when I'm typing. All right, let's talk about primes. So I can talk about primes if I want a list of primes up to 100. I can do that, or I can talk about primes in an interval using Magma. So I can talk. Yep.
Can you move the Magma box a little bit over to the right? Part of the WebEx screen plus minus buttons are covering up the middle. Yeah, that's much better. Okay, great. Now I can see them.
Is that good?
Yes.
Perfect. Thank you. All right. So I can do an interval of primes between 10 and 100, or between, let's say, between 100 and 1,000 prime, and between 100 and 1,000, it gives me a list. I can call that list if you want something, and then I can call the elements in this list like that. By the way, here Magma, the first element of a list is the first element of a list, unlike in Sage, because we were using some sort of Python code. So here, the first element of a list is the first element of a list. Nice. I can also talk about random primes in the database of primes that they have. So if I do a random prime, it gives me an error. I need to give it a little bit more information. So if I do random prime 100, it actually looks for a random prime that is less than 2 to the 100. Okay, so that's one random prime that I can use as a seed in some algorithm, or just because I I like looking at random primes. Okay, let's do another one. And there, another random prime. Perfect. I can do lists in Magma. Let me go here. Boom, 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 and I can copy and paste that. So you see, I defined n to be 100, and then I'm making a list of primes such that, well, primes in the list, primes up to 100, such that, what does this mean? Is integers 4, remember those were integers modulo 4, so it's a prime, so I'm considering p mod 4, and that has to be 1. So this list is the first primes that are 1 mod 4 in our list of primes. Okay. What else can I do? There are many elementary number theory functions. So I can do the divisors of 12. I can do, if you just want the number of divisors of 12, there are 6 such divisors. The number of divisors function came up, I think, in Brandon's talk. So you might want to do that. Something that also that came up in Brandon's talk was the Mobius function, the Mobius function mu. So the Mobius function mu of 12 is 0 because, well, there's a factor 4 in there. The Mobius function of 11 is -1, while the Mobius function of 10 is 1. Very good. Let me do a little bit of, as I said, the number of divisors came up in Brandon's talk. So let's do, let me show you how to do a for loop to calculate a sum of number of divisors. So this function, you see what I did is I started with a little variable sum, which is going to be 0 to start with. And then I added to that the number of divisors of the numbers I from 1 up to 10. And that's how you do a for cycle. You do for a variable, a counter from 1 up to 10, do, and then you tell Magma what to do. And then you have to close the end, the for loop. Remember that in Sage, you actually do not close loops, if loops or for loops, because the indentation in Sage tells you that this is over. But here the indentation doesn't matter. It sort of knows already it's a for loop, and you have to close the for loop before you start. So it actually already did the sum for me, and the value is 27. Right? I can, if you don't like that, if you're going to do that several times, for example, if you're going to try to plot, which I can't plot here, but if I want to find the values of this function of the sum of the number of divisors of numbers 1 up to x, you might want a function that tells you that. So here's how you can do a function in Sage, in Magma. That's the same function that I did above, but now this is going to be for any n, this is going to work. So if I do the sum of the number of divisors up to the number 10, I should get the same result I got before, but now I can do the sum of the number of divisors up to 100, and that's 482. By the way, the little Magma code text file that I have here, my cheat sheet here on the right, that I'm going to post on the CTNT website after this talk. What can we do? Other things of number theoretic nature is that I can do things like the Legendre symbol. By the way, also in Magma, I can do tab, and it will complete. Okay, first do Legendre, because then there's several Legendre things. And then if I do another tab, it's going to tell me, well, you have some choices. Which one do you want? I want to see what else is there. So I'm going to, I think, cut off some options. But anyway, bad syntax. Yep, I know. So it's what I'm looking for is the Legendre symbol. So the quadratic reciprocity symbol, the quadratic symbol for 2/7 For example, that's 1 because 2 is a square mod 7. The Legendre symbol for 5 over 7 is -1 because 5 is not square mod 7. If I do the same thing, but I put a 2 in the denominator, then Magma should yell at you like I yell at my undergrads in number theory when they put a 2 in the denominator of a Legendre symbol, because that is not okay. That the Legendre symbol is not defined for the prime 2. However, we have extensions of the Legendre symbol. The Jacobi symbol is implemented in Magma. The Kronecker symbol is implemented in Magma. And I can compute the Kronecker symbol of 7 over 2. Remember, the Kronecker symbol came up if you watch the video that I posted about the LMFDB when I was playing with Dirichlet characters. We looked at a Dirichlet character mod 4, and that was defined by a Kronecker symbol. So that is important. Okay. Other things that are important is I can check quickly if a number is a square free. Yes, 10 is a square free. 12 is not a square free. All right. So let's move on to something else. Unless there are questions, and please do let me know. Just stop me, and Brandon can ask me questions or give you a microphone. Let's do some p-adic integers. So here is the p-adics, and in Magma are defined by p-adic rang. 7, that's the prime, and 20 is the precision. So let's see what happens if I yell at Magma, hey, I want a third as a p-adic integer. Boom, what is this? So it tells me actually what is a third up to precision 7 to the 20 as an integer. So it's put all the powers of the unit and then the coefficient of 7 squared, 7 cubed. It's added all up into one integer, and that's how Magma stores p-adic integers. Okay, I can also do, let's do a p-adic field for 7 and 20. So I can do something like, now I should be able to talk about 1 over 21. And now you see that it's, yep.
For the p-adic, for the 1/3 in Z7, you're saying that it writes out the base 7 expansion out to 20 and reconverts it back into ordinary integer that might be negative?
Yeah, I don't know why the negativity, but it's an integer that is congruent to what the beginning of the expansion is in up to 7 to the 19 term.
The number it outputs is some base 10 thing. It's not even intrinsically like base 7 digits or anything.
No, and it's intrinsic. It's just an integer in base 10. Correct. Yep. So other things that we can do is that if I think this came up in a couple of the courses, maybe Liang and even perhaps in Keith's course, we can do Hensel's lemma in Magma. We can do Hensel's lifts. So for example, let me define a polynomial ring. So I'm going to define a polynomial ring. Remember that in Sage, you have to put this little dot here between the P and the bracket X. So here there's no that, but then there's column equal. And I'm going to define a polynomial ring over the field Q7. And then I'm going to do a Hensel left of a polynomial x cubed plus x plus 5. So you remember that, so in here, so this polynomial has a root. If I put modulo 7, if I put x equals 1, I get 0 mod 7. So we can try to see if there is a left of the number of a root that starts, that is 1 modulo 7. So let's see what happens. It should come from the same rank. So let's maybe what happens is that I should put it in the field, and it gives me a root. So it tells me that there is a p-adic integer, there's a 7-adic integer that is a root of that polynomial, and this is the beginning of the expansion.
Hey, Alvaro?
Yeah.
There's a question. Somebody's asking, what's the difference between p-adic ring and p-adic field?
P-adic ring, so yeah, so in the p-adic ring is Z7. Okay, so let me just write it here, but this is not going to compile. So Z is actually Z7 is the ring of p-adic integers. So things that start with 1 plus 7 plus 7 squared plus 7 cubed and so on. But there are no, you cannot divide by 7 in that ring, while in the p-adic field, that's Q7, meaning that I have the ring of integers and I've inverted 7. So that's why when I did 1/21, the expansion allows for a denominator of 7 in the expansion. So the difference is between Q7 and Z7 and the integers mod 7. All right. I can also do, if I want, I did a Hensel's lift, I can find also the same information if I factor the polynomial x cubed plus x plus 5, and then it's going to give me not just that one, but it's going to give me all the possible roots. And what this tells me is that this polynomial, there is one root in Z7, but then there's a quadratic polynomial that does not factor. So this quadratic polynomial would give me a quadratic extension of my of Q7. All right, let me see. I can also factor. So what happens if I try to factor x squared minus 5? Nothing happens. X squared minus 5 is irreducible in Q7. So I can do an extension. So so 5 is not a square modulo 7, but it's not divisible by 7. So if I adjoin the square root of 7 to Q7, I'm going to get a and ramified extension of Q7, which is in fact the unique and ramified extension of Q7. So if you want to talk about local fields, so an extension of a p-adic field of Q7, here's how you would do it. I'm going to extend Q, remember which was Q7. I should have maybe called it Q7 instead of Q. And I'm going to extend it by this polynomial, meaning that I'm adjoining a root of that polynomial. And Magma now knows, there you go, that L is the unramified extension of the 7-adic field defined by that polynomial. Okay, see that I didn't mention a generator, but I could have done that. Let's call it A. So I can call it A and then now extend by x squared minus 5, like that. And then now I can do arithmetic with A in my p-adic field. Okay. All right, let's switch gears.
Hey, Alvaro, we got a question before you do that.
Yeah.
The question is, how about factoring a polynomial f of x in the ring of polynomials with integer coefficients into irreducible factors?
Just over the integers?
The question just reads just over the integers, but if you can answer the question over like the p-adic integers or the p-adic rationals too, I'm sure that would be interesting.
So wait, so I did factor this polynomial x cubed plus x plus 5. I did factor it into irreducible components, into irreducible polynomials over a p-adic field. So I can also do the same thing, but over the integers. Polynomial rank over the integers, and then see if maybe this polynomial factored all along. over the integers, and that's why we got a root. Now, this polynomial is actually reducible over the integers, but over the 7-adic integers. So if I change again my rank and put here z, which stood for 7-adic integers, and I try my factorization, it does factor over the 7-adic integers into a quadratic and a linear factor. I hope that answers the question. Okay, I'm going to move to number field. So I'm going to just do polynomials over the good old integers. And let's see that, yes, now we are in the world of the integers. So here we are. And let's do an extension. Okay, so I'm going to extend the integers or the rationals by a square root of -5. So here we go. I'm going to define a number field by that polynomial extension, and there you go. So it gives me that extension. Oh, I wanted to mention something. Maybe let's start with 3. Let's start with 3, because if I do the same thing, if I define this, so this will be the number field defined by x squared plus 3. So it's q adjoint the square root of -3. Let's see what is the discriminant of k minus 12. What? No, that's not true. The discriminant of q adjoint the square root of -3 is not -12, it's -3. What happened? What happened is that can be very computing intensive to compute a discriminant. So it is actually just doing the discriminant of the polynomial I used to define the field. This is confusing to me, but what's happened is that I did not compute the discriminant of the maximal order of the range of integers. Okay, the maximal order is the range of integers of k, and then if I compute the discriminant of O, then it's -3. Okay, this is a little bit confusing. You have something to watch out for, so that's why I wanted to mention it. All right, let's go back to q adjoint the square root of -5, because I want some non-trivial class group floating around. So the factorization of f, this is just irreducible. And then I'm going to define k. So now k is a q adjoint the square root of -5. And let's see that I can change my rank like this. So what I did there is that now I changed the rank of definition of that polynomial to an extension. So I extended the rank of the field of definition of that polynomial to q adjoint the square root of -5, and then now my polynomial is called y squared plus 5, and then I can try to factor it. This is called fk. Wasn't it? Oh, f capital K. And there you go. So now remember, A here is the generator of q adjoint the square root of -5. So A is the square root of -5. And now it's giving me a factorization in the quadratic field of that polynomial. Now it factors. I do have the roots. Again, I can define the maximal order, and I can do the discriminant. That's correct. It's now -20. I can do a basis of O. And that's not very useful. Thanks, Magma. But so the basis is just is the first basis element and the second basis element. All right. You have to prod it out of Magma. What is it? O1 is just the number 1. And for O2, we can check what is the second element in there. I can do O2. And that is the minimum polynomial is x squared plus 5. So the second element is what we called A, is the square root of -5. So the range of integers is 1, square root of -5, or generated by 1 and a square root of minus 5. Something that you might want to do is factor ideals. In if you start a course in algebraic number theory, well, in number theory, we like factoring natural numbers into primes of the integers. In algebraic number theory, once we have a ring of integers and I have a prime ideal, I like to factor it into its, when I have an ideal, I would like to factor it into prime ideals. So I can do that by do a factorization of now 3 times O. That is the ideal, the principal ideal generated by 3. And it turns out it splits into 2 primes. If I do that for 5, now it turns out that 5 splits into 1 prime to a square power. That means it's that we call ramified prime. This 2 is the multiplicity of that prime. Here for 3, there were 2 primes, to multiplicity 1, the prime above 5, the multiplicity is 2. Let's do one more. What happens if I do, oh, by the way, another way of calling those ideals is the ideal generated in O by 6. So that's a principal ideal generated by 6, and that one factors like that. Okay, all right. Let's do some class group calculations. So the class group, G and map is going to be the class group of K. Okay, so the class group being the quotient of fractional ideals of my field modulo principal ideals, which gives me a measure of how far are we from being a PID, how far is the ring of integers from being a PID. So here I can calculate that we are 2 away. So it is not a PID, but it's a quadratic. The class group, there is a class, one class of ideals, of prime ideals, that is not, that they are not principal. Okay, so let's try to find some ideals that are not principal. So I can look at, well, what are the generators of my class group? And again, Magma is not extremely helpful. It just tells me, yes, there is one generator. All right. That's where that map comes from. So in Magma commands, there are commands that the output is more than one thing. So class group tells you the structure of G as an abelian group. So it will tell you, you can query things. Oops, that's a Sage command. So you can do things like this about groups. Is abelian, of course, is a class group. Yes, but that is giving you the class group as an abelian group. So if you want to actually relate it back to information about your number field, then you need that map that connects now the elements as an abstract group with actual ideals. All right, so remember, so I have G1, G1 is G1, but if I use my map that came from that command in Magma, the second output of that command, now it gives me an ideal of O, which is an ideal generated by 2 elements. So that is, let's call it something. By the way, if I call this ideal $1, that's the previous output. Okay, so that's I, and then I can do the norm of this ideal just to see this is an ideal above what prime is an ideal above 2. Remember that 2, oh, did we do that? Maybe we didn't do this. How does 2 factor? 2 is ramified also, so there's one ideal above 2, but like the factorization of the ideal 2 is 2 equals the square of a prime ideal. So that prime ideal, I, is not principal. Okay, so let's see other ideals. Let me define the ideal I1. This is an ideal O. I'm going to do 0.1 plus 0.2 and 3. So this is an ideal above 3. Let's see what it says. Yes, that's an ideal above 3, and I'm going to do the same thing, but an ideal above 2. Well, I do have it. That's an ideal above 2. And then I'm going to send them back to the class group. So the map goes from the class group to ideals, that map that Magma generated. So the inverse map will bring ideals back into the class group. And you see that I1 is non-trivial in the class group, is a generator of the class group. Let's see what happens with I. So the prime above 3 is not principal. This prime above 2 is not principal. But let's see what happens if I call the ideal above, the ideal generated by 6. The ideal generated by 6. I think I put one parenthesis too many. Is 0 in the class group. Of course, 6 is principal, so it will give me that is trivial in the class group because is the quotient over principal ideals. Okay. Let's look at some other. Let's compute some number field with a large class group. How do you do that? We don't know a good way to find number fields in general with large class groups. However, for quadratic fields, we know how to do it. That's something called Gauss's Genus theory. And it tells me that if I adjoin a square root of a prime, a square root of a number with a lot of prime factors, so for example, like this, then Genus theory actually tells you what the 2 part of the class group is going to look like, or like the 2 torsion of the class group is going to look like. So if I now call G is the class group of this quadratic field, then there should be, well, first of all, is it, say, abelian? True. Is it cyclic? False. What is it? Remember, we had this issue in Sage. I didn't quite know how to find elementary divisors of this. You can do so. You can do it in Sage, but if you have a group first, you have to say, okay, this is going to be an abelian group. And then once you have defined it as an abelian group, you can do elementary divisors. In Magma, that comes right out of the box. You can call for the elementary divisors of an abelian group, and it tells me that the elementary divisors are 2, 2, 2, 2. Even better, remember groupnames.org. You can actually call for the group name in Magma, and that will tell me that the group name is the cyclic group of order 2 to the 4th power. So it's Z mod 2 cross Z mod 2 cross Z mod 2 cross Z mod 2. That's the order of my class group is 16. So this number field has a large class group, and I could try to find ideals that represent every class. And well, Genus theory actually also tells you representative, so I don't need that. But I'll ask you in the exercises to compute classes of ideals that represent every class, or a basis of generators of the class group in this case. Okay, let's do some curves. Let's go to do things related to what Somia was doing yesterday. So we can define very similarly to what we did in Sage. I can define an affine space over GF37, not 27, GF37 2. Okay, so that means is the affine plane over a finite field of 37 elements. And I'm going to define a curve. Let's say now the space comes first, and then the polynomial, I'm going to define this curve, x cubed plus y cubed equals 2. So it's the locus of the polynomial x cubed plus y cubed minus 2. All right, I can compute the genus. So that's the genus that that Soumya was talking about in terms of the dimension of space of holomorphic differentials. So there you have, it's genus 1. Remember that elliptic curves are smooth curves, projective smooth of genus 1 with at least 1 point. So let's check if this is an elliptic curve. So I can check, I believe, is this smooth? It's singular. False. At least this affine patch, I'm not sure if it's checking yet the projective, so we'll check next in projective, but at least it's in affine. This is non-singular, and we have a point. We have a point because 1 plus 1 equals 2, so 1 cubed plus 1 cubed equals 2. So at least I have 1 point given by 1, 1, right? And you can actually try to call now an elliptic curve. So there is the same, like in Sage, I can now try to build an elliptic curve that would give me a Weierstrass equation for it if I have a curve that is smooth, genus 1 with at least 1 rational point. If I pass along the curve and the point, it should give me an elliptic curve. However, that's not how Magma works. That's not how this works. You have to give it in projective coordinates. So let's switch up to projective. Okay, so I'm going to do, projective space over GF 37 dimension 2. So it's a space that's a plane, a projective plane, and then I would define a curve in this projective space, x cubed plus y cubed minus 2z cubed, and here is the point. Now in projective coordinates, that's the point 1, 1, 1, and now I should be able to call an elliptic curve. Yep, that's this elliptic curve over GF37. It found the elliptic curve. By the way, I can do better. There should be a mappy here that is passing along, and then this mappy gives me the morphism that goes from my elliptic curve by my genus 1 curve that is not in Weierstrass form to the elliptic curve that is over the same field but in Weierstrass form. Very nice, and you can go back and forth with the map to find points on this side and bring them to the other side, and vice versa. All right, so that's the elliptic curve. Very nice. But how, in algebraic geometry, how do we know that there is a Weierstrass model? The proof, for example, in Silverman's, or I think is also in Hartshorn, there is one way to do this is using divisors, which I, at least yesterday, Soumya started talking about divisors and divisors, the class group of divisors, the Picard group, and so on. So let's do divisors with Magma, just so you see the beginning of how to start doing something like that in actual computations. So I can define the divisor group of C, C being the curve in not Weierstrass form, and I can compute the divisor group. I can also compute the class group of divisors, so divisors modulo principal divisors, and it will tell me what is the structure of that group is infinite, and there is some torsion and so on, and you see, class group passes along 3 things. The third thing is the map that goes between generators of the class group and divisors. So let me see who is the first generator. If I do this at phi, it will use the inverse map to actually compute a divisor. What does that mean? Let's say, what is let's call this divisor D, and then do the decomposition. of D just to see what kind of divisor is this. And it's a divisor that is, the support is at 2 points on the curve, at 10, 10 and 23, 2. And it's this with coefficient 1 and this with coefficient -1. So it's a divisor with a 0 and a pole. Okay, and it's a degree 0 divisor. All right, what else can I do? I can do a canonical divisor of my curve, and it is a divisor, so not great news there. But I can actually do the decomposition of my canonical divisor, and it's a place. So it's a decomposition now. It's supported in 4 different points, like that. Okay. What else can I tell you? Oh yeah. So in the proof, to find a Weierstrass equation, the proof goes by the Riemann-Roch theorem, and uses what's called the Riemann-Roch theorem and these Riemann-Roch spaces. So let me first build a space. Let me first build a divisor. So I'm going to build a divisor supported on 1 point. Okay, so I'm going to pick a point. Remember that P was the projective space. Maybe it's okay, I think, if I get rid of it. So P is going to be the point 1, 1, 1 on my curve. Perfect. And then here's a place. The places, what places are there above this point? The places are what the divisors are supported on. They are called places in Magma. And I'm going to call D a divisor. So this belongs to divisors, and is the places above, supported above this point. And there is only one such place, so it's just the first such place. And then D is a divisor exactly supported at 1, 1, 1. And then I can compute a Riemann-Roch space. A Riemann-Roch space is a space of functions. This divisor is supported at 1 point, so this is a space of functions that have a pole of at most. The worst thing they can have is a pole at that point P of order 1 if I do exactly this. Sorry. Okay, so it turns out that it's a module of dimension 1 over GF37. So it has dimension 1. What does that mean? Let's call it something. So V1. Yeah.
There's a question real quick.
Yeah.
So John is asking, what's the range of objects that you can use as C in this code? Could you replace C with something like a projective variety, or like what are the options?
Oh, you can definitely replace. You can write. Yeah, you can define varieties, and then, but I don't know. Not off the top of my head, what sort of like functionality you're going to have with higher dimensional varieties. You can definitely define varieties by a sequence of polynomials in higher spaces, higher dimensional projective spaces, and there should be some functionality. We can explore that later during the break. All right, let me see if in the last 3-4 minutes I can do some Riemann-Roch here. So the Riemann-Roch is a vector space, and it comes also with a map. It stores V1 is a vector space, it's an abstract vector space. So if I try to just say, what is V1? It's just going to tell me that. And if I ask, what is a basis of V1? It's just going to tell me, well, it's one-dimensional. What are you asking about? There's one vector in there. However, if I call that B1, I can use my map 1 on B1, 1 on the first basis vector to compute a function. Okay, so now it's a function in the function field of my curve, and it's actually the function equals 1. Yes, because we know that those functions do not have poles, so they are in the space of on that Riemann-Roch space. Let's look at other Riemann-Roch spaces. Let me do the same thing, but with the Riemann-Roch space for 2D. Okay, hold on. So here it is. Where does it start? yeah, here. So I now define V2 to be the Riemann-Roch space for 2D. So now I'm allowing poles up to order 2 at that point. And now it's a 2-dimensional vector space. And thanks to my map 2, now I can find functions on my function field that this new function has a pole of order 2 at that one point. This one point is the one that is we're going to use as the order of the origin, and it's going to give me the structure of abelian group later on. So anyway, I don't want to spoil that Riemann-Roch theorem for you and the how you find the Weierstrass equation, but once you start reading through Silverman, the fact that 6D has dimension 6 is exactly the key ingredient in that now all of a sudden I can build all these functions. I can build more functions that I could account for, and those functions are going to have necessarily a relationship that is going to give me a Weierstrass equation. Okay, so I think it's already noon, so I'm going to stop here. So what we will do next time, tomorrow, we are going to do some heavy-duty Magma computations on the screen. First of all, we're going to verify the Birch and Swinnerton-Dyer conjecture. So we're going to talk about the Birch and Swinnerton-Dyer conjecture a little bit and just see what it says. And then we're going to numerically verify the Birch and Swinnerton-Dyer conjecture in a few cases where there is no SHA, where there is SHA. Then we're going to talk a bit more about how to compute the Mordell-Weil group in general and what algorithms we can attempt using Magma. There is a very rich variety of things that one can do, and Magma is very powerful in that sense, but still we're far from being able to compute Mordell-Weil groups entirely. And then if I have time at the end, I will try to find points on other varieties or points on curves of higher genus, which is quite a challenge, but in some cases we can succeed and win. So I'll stop there. So thank you.